And the first talk is by Professor Sergei Suslov from the Arizona State University. And the title of the talk is Kepler Problems and Sommerfeld Puzzle. Please.
Good morning. Special thanks to those who are survivors of this intense workshop, right? Intense workshop. So I would like to talk about kind of historic matter. As you know, 1924, 25, 26 is the years of creation of 100 university of creation of quantum mechanics. First it was matrix mechanics by Heisenberg and other people, and eventually 25, 26 it's Schrödinger. But at the same time, there was a huge experimental database starting even the previous century, right? And it was a remarkable coincidence. Sommerfeld pretty much found the formula for relativistic hydrogen atom. In the process, he also formulated what we nowadays call Bohr-Sommerfeld and Wilson probably quantization rule, old quantum mechanics. Okay, so this is what actually I'm talking about. Sommerfeld, 1916, found remarkable formula which agreed with experiment about energy level of relativistic hydrogen atom. And this is called Sommerfeld puzzle. And every decade somebody is discussing this thing, right? And I decided to introduce my 5 cents in this sense because I disappointed with the previous discussions as well. Arnold Sommerfeld is a great mentor of Nobel Prize winners. 7 his own postdoc students won Nobel Prize. He himself was nominated 84 times. As far as I remember, it's the largest amount of nomination in the history of Nobel's committee, but unfortunately he didn't get prize. And this is not a full list because it also, there were dozens of another people who were leaders in their area of research. Okay, so I will talk very about brief history, WKB method, exact solutions, Sommerfeld puzzle. Well, I probably should put resolution in also in that one. And example, historical comments, and a little bit of bibliography. Okay. Well, I always used to like to my students that formulas are smarter than people. And usually get an example, quadratic formula, say, look, quadratic equation has 3 parameters, right? In all your lifetime, you will never solve all possible cases, right? But later on, I found this citation. One cannot escape the feeling that this mathematical formula have an independent existence and intelligence of their own, that they are wiser than we are, wiser even than their discoverer, that we get more out of them than was originally put into them. Who said that? Well, it was Hertz about equation, Maxwell's equation, okay? And we all remember that he was discoverer of electromagnetic wave, and obviously it's one of the consequences of Maxwell's equation. It's much stronger than my actually statement about quadratic formula. Okay, brief history. You probably do not know that fine structure of hydrogen atom was discovered in 1887, but Michelson. So we all remember experiments of Michelson. I think it's about 1904 or something, that speed of light does not depend on the frame of reference, right? But the first experiments were done at that time. Probably accuracy was not good enough. So when he failed, he didn't find effect of this Acer wind, he switched to the spectroscopy and found indeed that leading Balmer series split in duplet. And again, it's remarkable discovery because we all know that electron was discovered only in 1997. What is it, 10 years after that? And Rutherford model of atom, 1911. Okay. Well, in 1916, Sommerfeld applied quantization rule and found the formula. So exact solution was obtained Darwin and Gordon in 1928. Dirac actually wrote in several recollections that he was afraid to solve this problem because he was afraid that, like Schrödinger, he will fail, right? So he decided first to publish free particle solution, but obviously other people found the solution. Werner Heisenberg also contributed. He even called it he called it a miracle. 1968. It was the year when they celebrated 100th anniversary of Sommerfeld birthday. Okay, so I would like to look at this thing from modern viewpoint because different authors, they're trying to use like a mixture, what we kind of pre-quantum mechanics and so on. Nowadays, I think that what we have to do, we have to use Schrödinger and Dirac equation, right, and to corresponding problems, right, problems. And nowadays, obviously, all these rules are a consequence of WKB approximation. Okay, so WKB approximation, we usually separate variables and we work with radial equation. A radial equation we consider of this kind. Of this one, you see no first derivative already resolved. It's like one-dimensional Schrödinger equation. But for this coefficient q, we simply assume that x squared by q is continuous, right? Well, unfortunately, it's known that this approach does not work for Coulomb problem at the origin, okay? Nonetheless, this is what we can do. We can make a substitution. Then equation changes, and you look at the new coefficient. It's some constant x squared q. Remember, it's resolution of this singularity. But once again, historically, it was suggestion by Langer only in 1937. So then you see, if you take this potential and go back to original one, well, you can see usual rules that you have to replace original coefficients q, -1/1/4 and so on. Eventually in central field, it will be so-called replacement by L plus 1/2, okay, squared. Okay. So, well, again, nowadays you can read best either in Nikiforov-Uvarov or Langer also, and so on. Now, it's convenient to combine all Coulomb problems in one kind of formula. And this is done, by the way, by Sommerfeld himself. So he used actually, wait a second. He used actually formula like that and quantization rule. And you see he used these parameters, A, B, C. Well, how to compute this integral, we'll say a little bit later. But if you combine these two results, then this is what happened. You see, your original coefficients A, B, C, they call from the Schrödinger or Dirac equation, and so on. And this would be already when we use this Bohr-Sommerfeld-Wilson also quantization rule. And all this potential, I suggest to call it Sommerfeld type potential, because Sommerfeld heavily used this united form in his actually book, 1928, and also even Schrödinger used in some lectures in the same form. And what is inside, it's not only a relativistic hydrogen atom, well, it's non-relativistic Coulomb problem, relativistic Coulomb problems, Kratzer molecular potential, and so on, and so on. So I would like to combine everything together and to discuss it first, how it works, and then to consider an example. Well, just in case, and it's not such a big deal to evaluate this integral. You can simply integrate by parts. So Victor was remembering our wonderful professors from Moscow Institute of Physics and Technology. Fedoruk was teaching ordinary differential equation, and he used to like to say that half of masses contains from integration by parts. parts. If integrate by parts, then both integrals can be evaluated, and here you go. Originally, obviously, Sommerfeld used complex analysis, so then you have certain cuts and so on and so on. This is half of the page from original Sommerfeld book. Okay, so this is roughly speaking, we got this quantization rule from WKB approximation, not from old quantum mechanics, but starting from modern view. Well, we already assume that either Schrödinger equation known or Dirac equation unknown, and we apply WKB approximation with Langer correction, Okay? And Langer correction, otherwise you cannot apply WKB. You can postulate, right? But you cannot apply, you cannot derive it from the exact. So now, what I call here Nikiforov-Uvarov method, but I have to admit it's taken from Nikiforov-Uvarov book. And in those days, 30 years ago, there was no any actually talking about Nikiforov-Uvarov method, right? It was one or two actually section in the book dedicated to the problems in quantum mechanics. But you see what happened. People starting to use these ideas, and eventually they started to call it this way. And I think Arnold Ferdinand would be very proud that you see now it's named after him. So I call it Nikiforov-Uvarov method of quantization of blah, blah, blah. So they actually managed to come up with the right equation, which can be transformed and then applied in quantum mechanics. Equation of the second order. Well, the second formula, it's written over here, but it's important to emphasize that sigma and sigma with tilde, it's polynomial of degree up to 2. Okay, quadratic polynomial, maximum, but also could be linear, could be a constant. And tau with tilde over here, it's linear polynomial. Well, obviously, WKB approximation, if you remember, there was no first derivative. This tau with tilde, in our case, will be zero. Nonetheless, what is the Nikiforov-Uvarov method? You can make a substitution. Okay? So instead of one unknown function, you introduce two more, right? Phi and y. But then you can use specific choice of function phi. It will be clear in the second, you see. And for y, we can get much simpler equation. Well, usually it's what we call equation for classical orthogonal polynomials for specific eigenvalues, right? And now you see second derivative, polynomial of degree up to 2. First derivative, first, and this is a constant. If you use, for instance, power series expansion, then the power is kind of keeps the same thing, right? Okay. So how about this function phi? Well, here we have to write a little bit of formulas. So phi, it's a solution of first order equation. Well, then we introduce some constant, and pi is supposed to be linear function, but we saw it as a quadratic equation. And here you go, you say it's ridiculous, right? You have to come up with a linear function, but you found for this linear function quadratic equation. What do? Look at this radical. It's supposed to be a complete square. This is the only way, right? Then you can actually get rid of this square root. And how to do that? You see there is an arbitrary constant k over here. By choice of this constant, we complete the square, and so on and so on and so on. Okay, well, all right. So then the final page, you see, we quantize. For quantization, we have equation. Remember before we had this equation in this coefficients AB. In this case, it's equation like that. Well, in our case, sigma will be first order, that this term actually disappear, right? And the square integrable solution, I'm only talking about discrete square spectrum, they're up to the constant classical orthogonal polynomials, which better defined together through the Rodriguez type formula. You can do it through power series expansion, then you'll have at least two formulas. That one is one. Okay. Well, one more thing, what physicists usually do not pay attention, but mathematicians sometimes do the good job for them, right? If you have actually infinitely many those classical orthogonal polynomials, that there is a uniqueness theorem. So, namely, if there is any other solution which is square integrable, which is square integral. Or I only talking about L2 solutions, right? Then Nikiforov-Uvarov did show that integral, this roughly speaking will be orthogonal to all actually system of solutions, and by corresponding theorem of completeness of classical orthogonal polynomials, they must be zero. They must be zero. Okay, so there is a completeness. It doesn't work if you have a situation when we have only discrete energy level, and to the best of my knowledge, nobody knows what to do in this case, you see anyway. Okay, so now you see we have to identify in this Nikiforov-Uvarov procedure the case which correspond to this Sommerfeld potentials. It's kind of clear that sigma must be x. First order, Schrödinger equation does not have first derivative, so this coefficient 0, and that one we take this y. Why? Because it will work. Okay, this is also y. So then we go to this formula for pi, we write it, you see, oops. We write it, and everybody can see that k is an arbitrary constant over here, arbitrary constant over here. So then, by choice of this constant k, we complete the square and come up with several functions of pi. This is also the nature of this Nikiforov-Uvarov transformation. We usually have not one answer, but four. But in the theory of special functions is good because it's nice to produce as many solutions as you can. So in this case, you kind of relate functional relations between different solutions or whatever. In quantum mechanics, it's kind of another way around, but usually you see in this particular case function tau, which is in this equation for orthogonal polynomials, is 2 pi. And we simply use this function, derivative of this function negative. This will fix actually our choice. Well, after that, if you put everything in this condition, remember, so we have the same equation, but I use lowercase ABC, AB. Oh, this is probably C. This is a mistake type. Okay, and now my resolution, you see that no matter how you use actually W approximation, or you try to find exact solution, right? The formula for the energy level is absolutely the same. So this puzzle is like what happened, right? Some happened. So you see, you compute something one way, you compute something another way, which is probably not exact way, but you're getting the same result. So this is what it is. Okay, so now you see, I would like actually to share with you some letter from Schrödinger. It's about 1954. He pretty much described this situation exactly how actually I explained it to you, but didn't write the formulas. Okay. See what he said. He said that Sommerfeld formula, it's actually an accident. So Sommerfeld has actually detailed information, experimental results, right? He actually has the clue how to pick his parameters. Right? Well, and he also liked to comment, they all like to philosophy, that you see in this is a case when the general theory goes far away from original one. Indeed, we know that quantum mechanics is quite different from classical mechanics and original rules of quantization. Then actually he's saying something which is extremely important for the history of science, that he did discuss even before publishing the first paper, what we nowadays call relativistic Schrödinger equation. It's what Klein-Fogg-Gordon equation he discovered. And not only that, he solved it for the relativistic Schrödinger atom, but got a wrong answer. This is what he's saying himself. I found that the formula doesn't match experimental data, and I switched to non-relativistic level, and everybody is saying, where is this particle of Schrödinger, which was taken out of the journal? Because archives of Schrödinger, they still do exist in Albach, right? So somebody has to find it. So that so far it was not found. That you see, once again, we have to understand that from this original idea of Sommerfeld, old quantum mechanics to Dirac equation, well, the science went to two revolutions. One revolution of Heisenberg-Schrödinger and another revolution of Dirac relativistic one. Nonetheless, the answer is the same. Okay, now just a few examples. So now I consider several, this is what I call Sommerfeld high potential, starting from non-relativistic Schrödinger equation. For hydrogen atom, everybody knows this result. So radial equation like that. I use dimensionless units, and because I use x variable, x is not xyz, it's renormalized r, radius. Okay, so you see our formula like that. The result is obviously Bohr formula, whatever. So the next one, this is what I told you, relativistic Schrödinger equation. Only two very good books on quantum mechanics, maybe Merzbacher book and Davidov book. They discuss this case. Well, the difference, I forgot to say, everybody knows that in this Klein-Gordon-Fock equation, the spin is 0. This is why Schrödinger originally failed, right? In Dirac, spin is 1/2, right? And everybody agrees that there was a revolution from this one to that one as well. So if you take this, but there are particles also with spin 0 in Coulomb field or whatever. So once again, in this case, we apply the formula. Well, we have this crazy parameter nu over here, you see, related this way. And the formula look like that. And I wrote here an expansion, non-relativistic expansion. As you can see, what was Schrödinger comment? He was talking about this term, right? L is angular momentum integer, L plus 1/2 half integer. And this was the difference with Sommerfeld formula. This is why he invented this equation. He solved it for relativistic hydrogen atom, not hydrogen, for spin 0. Instead of electron particle with spin 0. He found this formula, he saw that it's wrong, and they actually reduced to non-relativistic case, and it was until a couple of more years when Dirac discovered his equation, and all these doubts disappeared, right? It was kind of puzzled for a couple of years why this happened, right? Well, also I wrote here something about each term. Well, obviously this is what rest mass. This is standard energy level. And that one, you see, usually in Dirac formula, we say that it's Pauli correction between spin of electron and angular momentum. But here you go, the formula is here, spin is 0, right? So I simply call it fine structure. You have to be very careful with this interpretation. There are no spins of the term with fine structure is here. Okay, I'm a mathematician now. I don't care about this. I'm just telling you, be careful with terminology. Okay, so what is next? Okay. Well, this is, by the way, original page from Schrödinger notebooks. Notebooks N1 or something. It only has 3 pages. But over here, this is a proof. One of these equations right here, it's exactly relativistic Schrödinger equations, the spin 0, which eventually Schrödinger rejected, right? Okay, and this is a lovely place when this discovery took place. I don't have time to discuss this romantic story or whatever, but you have to be careful. This is a Nova Day picture, and this is Arosa. This is a building when Schrödinger stayed. And that one, it's a newer construction made where house of the owner of this, it's tuberculosis sanatorium in this case. So you see, to prove this is an old picture. You see, this is what it is. This is the house. Because in famous biography of Moore, I believe that the picture is wrong over there. You always have to watch, even after historian of science. They're not always correct. Okay. Well, finally, let's talk very briefly about Dirac equation, also not written very well in the literature. So we start from Dirac equation, we go through the standard procedure separation of variables, which is non-trivial, by the way, It probably will take 40 minutes to explain what it is. And we end up with couple of equations. Actually, it's two radial equations. There are certain substitution, but I write it in convenient form. Actually, over here, I even improve a presentation in Nikiforov-Uvarov book, because here, once again, it looks like one-dimensional Schrödinger equation without first derivative. Okay? So there is a second equation. It replaces formally nu by minus nu, but we know the answer, big spinor and small spinor, right? And we are looking at non-relativistic limit, so it doesn't make any sense, at least originally, to discuss second equation. We just concentrate on those which survive. Whatever. Again, after Alger transformation, you see we have this correction. How the people work without this transformation 1937, I do not know, but somehow miraculously they knew how to put right actually correction. You see? And after that, this is a Dirac formula. And in Dirac formula, you see there is a different parameter nu. You see, and J over here is total angular momentum, which consists of spin and so on, addition of spin on half. So once again, I write this formula for Dirac, and you see, because look at the second term, J is now half integer, so this becomes integer. Okay? So once again, in this case, we can say, you see correction, Pauli approximation, which exclude interaction spin and its orbital momentum. But I pointed out that in the previous case, right, when the spin was 0, this term is also here. Okay, so we have to be careful with this terminology. Okay, and this is why. If you consider the spread, right, in Schrödinger formula, which never was published by Schrödinger, right, but nowadays in the Davidov book and Merzbacher book. And Sommerfeld formula, you see, the distance is 8/3, so Schrödinger is much wider, much wider. And this is why Schrödinger never published this article, because he was actually true theoretical physicist, right? Did experimental work, is definitely was wrong, you see, in his opinion. Nowadays we know that it's spin 0, but the concept of spin appeared exactly at the same time. And it's a lovely story about that one, but I don't have time to talk about this. So finally, one more example, it's so-called Kratzer molecular potential. Also, it was introduced about 1920s in old quantum mechanics. And in this case, once again, we only have to figure out how to switch to dimensional things, right? This is our equation, A, B, and C. This already take into account our Langer transformation. This is why L plus 1 rigorously is replaced by L plus 1/2 squared. And after that, we have once again similar formula, and parameter mu is the shift and so on. I don't think that this potential works very well for biatomic molecules, but historically it's probably one of the first ones. Okay. Well, now I have very little time to review remarkable articles which have been, how much time do I have? 5 minutes? Okay, so first of all, obviously, nobody knows that before Sommerfeld, Bohr-Sommerfeld quantization rule, I believe Bohr doesn't have any actually to do with that. It's actually Wilson and Sommerfeld. And Wilson was a little bit earlier, a few months earlier, publishing. And Sommerfeld in his books cite Wilson, but then he said that he never applied it to relativistic Kepler problem. Okay. So there are a couple of very good, actually, historic reviews. This lady, I think she's from Sweden. She wrote so many great articles as historian of science about the history of quantum mechanics. I definitely recommend Physics Успехи, UFN. You see, wrote actually Milantiev, I believe his name. He wrote in 2004 wonderful article about history of Bohr, and again you will be surprised actually how much Bohr actually already, well, these ideas they have been in astronomy, roughly speaking, right? So. Okay, Schrödinger, you see, in 1 year he published 6 articles. You see, American Mathematical Society published the little book. It's all there. This is my gift from American Mathematical Society to our, actually, Professor Dodonov, right? Vita, it's for you. Oops. Sorry, guys. Shit happens. Yeah, no problem. This is good. I got it. Okay. So now, well, we wrote some article recently about history of discovery, and again, I'm report gliding that it's on the top of the most read articles for about a year and a half, and so on. You see. Okay, this is about Dirac equation. Obviously, Dirac article is 1928. There was another one. It's a free particle, and I told you that Dirac decided not to solve this relativistic hydrogen Kepler problem because he was afraid later on, he was saying that the answer once again will be wrong. And in this case, following Schrödinger example, he will not have to publish that. Well, the problem was solved relativistically by Darwin and Gordon the same year. And Dirac also has many recollections. This is a couple of those, very interesting, especially for students to read, you see. Well, all these people, creators of quantum mechanics, it was top of their career, right? Schrödinger obviously never did anything of that level, although he worked very hard. Dirac, the same thing. Well, Heisenberg, he was younger, he still contributed something, but it's another story, right? Nazi history. So about Heisenberg, Sommerfeld puzzle, you see, I'm not original. You see, Bidenhard already wrote an article when he claims that it's also rebels, but he is in honor of Professor Wigner on the 80th birthday. I said it's too late to wait for another 5 years, so I decided to say something for 75th birthday of Professor Dodonov. Okay? All right. So, and this is always discussing. Granovsky wrote an article. There is a philosophical aspect to this problem. You see, Petrov is arguing with Granovsky and so on. Now you also have my little comment. So Nikiforov and Uvarov method, it's kind of from the book Nikiforov-Uvarov, which is probably the best book for practical purposes, for physicists, right, on special functions in these applications. Right? Well, we wrote a couple of articles, and including our last one, when we roughly speaking all potentials which can be integrable, like from Flügelbus, where there is a discrete value. We put them together and did outstanding job also. We wrote supplementary Mathematica file. Usually everybody knows that calculations are pretty lengthy. Okay, it comes with Mathematica file, and one of our, well, these two people, it's my students, and Christoph Kuchan, it's superstar in Mathematica. You see, though this is done very, very well. It cannot be better done. I mean, Mathematica file. Because when I look at all these books which claim that they're using Mathematica for quantum physics, it's not at that level. Well, finally, we are on quadratic systems. It cannot match in classical work by Dodonov and Manько. Well, there were others, but this one, I think, the most actually known in English. Am I right? So this one, well, unfortunately, their book with Malkin never been translated to English for some reason. I don't remember. And we also contributed something. You see, this is our several articles. If somebody interested, we did something. You see, at the highest, I believe, mathematical level. And so on. You see lots of those. Just part. Okay. So finally, I would like to thank organizer for this kind of invitation. I'm very proud to talk about this topic over here. I acknowledge the help of my friend Rodrigo Plata, our Brazilian faculty member, right? he introduced us to the beamer, right? And finally, thank you so much.